So welcome to the last of the videos about Hilbert's basis theorem. We've set up some preliminary stuff in the earlier videos, and now we were going to prove Hilbert's basis theorem, but I've just ploughed through it, and there was a couple of things which I found were missing, and so let's start by filling in these things first. These should really be in another video, but rotten luck. We want the if P and Q are polynomials, we want the degree of P minus Q is at most the max of the degree of P and the degree of Q. And we have the corresponding result for adding polynomials. And so I'm just going to add the negation, as it were. So let's convert polynomial dot da, 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 da. So this wants a P and a Q, so I'm going to give them P and negative Q. And then it wants two proofs. No, it doesn't. So unfortunately, it's simplified things too far. It wants us to prove that Q is negative Q, which is not true. So why don't we do using 1 or something? That looks good. What about using 2? Can we get away with that? Ah, bingo. Perfect. So now we've got to prove that the nat degree of Q is equal to the nat degree of negative Q, and hopefully that's the simplifier knows that it does. Let's see what that's called. It's called nat degree neg. So let's just rewrite. I mean, it's just going to be exact this, presumably. Or we could apply it. Exact degree neg Q. Oh, we got the wrong, yeah. We need to apply ec.sim, so how about we do that? Bingo. So that's the end of that. And now this one, if the degree is bigger than 0, then the leading coefficient is non-zero. So past me suggests I use this, so have h1 colon is this, and what does that say? H1 colon says if the degree is equal to something, then so maybe I can just apply this, and now I've got, you see, now I've got now I need the fact that the nat degree and the degree are the same, so this should probably be, let's see exactly what this says. This says if something isn't 0, then the degree is the nat degree. I see, so the next thing is that I can rewrite HPN here, and now I can apply this there, and now all I've got to do is prove that P is non-zero, but P is non-zero, I mean, so now I could do Rintro Ruffle, I suspect. Yeah, and now I would imagine, and then case is HPN or something. There we go. So there's a bit of a hack. Rintro Ruffle defined P to be 0, so I actually changed HPN. And 0.nat degree is definitionally 0. So HPN says 0 is the successor of something, and that somehow contradicts the way that the natural numbers work as an inductive type. So there's a slightly hacky proof of that. And now what? Let's get on to the proof of Hilbert's basis theorem. So, I mean, I discuss the strategy in the comments. So I've got to prove that, so we know that R is Noetherian, and we've got to prove that the polynomial ring is Noetherian. So let's rewrite this. And now I've got to prove that all ideals are finally generated. So intro I. Okay, so now what? These are definitions we have. Right. So this, I think, says that we just need to get an n. So let's have colon is this. Oops. Well, that happens. This says there exists an n, so I think I want to obtain NHN can be this. So I mean, I'll let you. I mean, this Orcs ideal is some ideal of R, and this Orcs ideal too is some other ideal of R. And these Orcs ideals are increasing, and HN says that they stop increasing by the point capital N. So now what? Aha. So right. So I think let's let S be. So I need to encode this concept in Lean. So it's going to be finset.b union. And now it wants a finset. And that's the finite set of. That's going to be finset.range n plus 1. And now I'm supposed to be giving a function from the natural numbers lambda d comma underscore. And that function, we take a finite generating set of the okay, I should call it I apparently. There. So this should be orcs ideal dot lift. Orcs ideal dot lift. That lifts. Aha, that lifts an element of R. Right, an element of R to an element of polynomial R. So I should give it. So what are we going to do? We're going to use map, right? We're going to use image. We need to do finset.image because we need to take the image of. So now we need a map and then we need a finset, and the finset will be the generating set. So I do finset.image of this map. What was it called? Orcs ideal dot lift, and then it wants an ideal, and it also wants a number, which is presumably I. And now I want to put something here. Oh, that's a shame. I see. So this is the function lambda r, orcs ideal lift IR. How about that? And it wants to know that something is decidable. So let's do classical. Wonderful. And now the one underscore you see I've got two goals now, and so what am I missing? I'm missing the finite subset of R, and that's the generators. So that's orcs ideal dot gens. If we can go over here, orcs ideal dot gens. It says it's never heard of orcs ideal dot gens, which is kind of interesting because I'm claiming that perhaps it's not called orcs ideal dot gens. Is it called hr dot gens? Yeah, it's hr dot gens. But now I have to say what we are taking the generator of. hr dot gens. What does this? Oh, how annoying! I can't see. Is Noetherian ring dot gens. Now if I hover over this, there, now I can see it. So it wants the proof that R is Noetherian, and then it wants an ideal. So now we want HR. And the ideal we want, orcs ideal II. So orcs ideal, capital I, little I. And this should be H capital R. There. Oh, and I'm slightly annoyed that that's not worked because I thought we were done now. What's the error? Is Noetherian ring dot gens? Oh, it's not because it's not in brackets. And now hopefully this will work. Bingo. So we've got one goal, and now we can actually simplify this because we can put this HR back here and use dot notation. There we go. So we look at the generators of the ith auxiliary ideal. We then take the image under the lift map. That gives me a bunch of polynomials, and then we take the union for I less than n plus 1, and we let S be that generating set. So that's the So that's the set that's going to work, right? Our goal. What's our goal? Our goal is that I is finally generated, so we can use S. Will that work? Yeah. And so now we've got to prove that the span of S equals I. And so first we're going to prove that the span of S is less than or equal to I. So let's have HSI. I claim that span of S is a subset of I because, oh, rotten luck. What's this ideal dot span? What was the goal? Yeah, ideal dot span. Oh, it doesn't like the. I should say that S needs to be considered as a set now. Oh, it's set polynomial R. Polynomial R. Are you happy with that? Yes. Now we've got two goals, so let's prove that the span of S is a subset of I, and so I guess we can apply ideal dot span LE according to the hint. So that's an if and only if, so we can maybe rewrite ideal dot span LE. That seems to have worked. Wonderful. And so now we should have reduced to the claim that S is a subset of I. Yes, it is. So now we can just do, I guess, intros SHS. So now we have S in this. So do you know what we could do rintros, and then HS says S is in the set. We could just do this. We could HS S is in S. Did that work? It did. Great. And so now, and so S is defined to be finset.bunion. So I can rewrite finset.membunion as HS. And so now HS says this, and so now we can take it apart. So our case is HS with whatever JHJ. And I've got to prove that S is in I. I mean, what about HJS? HJS now says S is in the image of that function there. I need the fact that Orc's ideal lift of something lives in I. And we proved various things like that in earlier sheets, didn't we? That's not it. That's something technical we'll need later in this proof. Here we are, lift mem I. So that's what we're going to end up using. So this is going to be apply this thing here. And it's never heard of it because it's called Orc's ideal lift mem I. And so it's complaining that it doesn't know that S is of the form Orc's ideal lift. So what does this HJS say? HJS says I'm in the image of something. I wonder, can I do, does that work? No, it doesn't. So let's rewrite finset.memImage then. Finset.memImage at HJS. And now that says there exists an A. You see, there we go. And now we take this apart because HJS now says that this is some lift. So, and so we can do our cases HJS with something RHR ruffle or something. There we go. And now you see the goal has changed because I put that refle there. I did this refle trick. And now I've got to prove that the lift is in I, and that we've proved already. So that is the easy direction. I've proved that the span of S is a subset of I. So now let's do the harder direction. Let's apply LE antisim. anti-sim. And that is a proof that if A is less than or equal to B and B is less than or equal to A, then A equals B. So we can feed in HSI, I would imagine here. Yeah, now we've got to prove the other direction. So let F be an I, intros FHFI. There, and now we're going to prove the result by strong induction on nat degree. And I must be honest, I had trouble working out how to do that, so I've dropped a hint here. The way one does things by strong induction on nat degree is like this, apparently. And now what just happened, so now we've got this HD that says if I've got a polynomial of degree, it's a bit clunky. We've got an underscore x and an underscore x and an n. Let me just do dsim at ht just to see what HD says. HD says if m is less than, so d is the degree of the polynomial. If m is less than d, and I've got a random polynomial, I mean, unfortunately also called f, so let's call it g. If I've got a polynomial g in I of degree m which is less than d, then I claim I is in the span of S. So I see. So it says I and the span of S are equal for all degrees less than d. And now I've got f of degree equal to d, and I want to prove that f is in the span. So that's the idea. We now have a hypothesis H saying the degree of f is d, yes, and a hypothesis HD says that, right, yes. I see. So in fact, we can put that d-simping there if we like. So how are we going to prove this? The idea is we've got a polynomial of degree d. I'm going to create a new polynomial g, which will also have degree d, and it will have the same leading coefficient as f. And the idea is I'll use that f is in I, but I'll make sure that g is in the span of S. So g is going to be in the span of S, and so g minus f will certainly be in I, but g minus f, the inductive hypothesis, will apply to it, you see. And so g minus f will be in the span of S, and we know that g is in the span of S, so we can deduce that f is in the span of S. So that's the idea. So we claim it suffices to find a polynomial g. So suffices, there exists g, a polynomial, such that g dot nat degree is less than or equal to d, and g is in the span of S, ideal dot span S set polynomial R. And g and f have got the same coefficient of x to the d, so g dot coef d equals f dot coef d. There we go. I claim it suffices to prove that. And so let's prove that now. That proof can go here. So then f minus g will have degree less than d, and we can use our induction hypothesis to show f minus g is in the span of S, and hence f is 2. Right, so in fact we could rewrite by ring. I claim that f equals f minus g plus g. That's a shame. I need to get g, so case is this. So our case is this with g, hg. And hg is probably lots of things. Yeah, hg says hg degree, hg is in the span of S, and something else that I've forgotten. The last one was the coefficients are the same. So there we go. Now we've got to prove that these two things are in the span of S, and we can just apply. You see, I'm just doing the proof backwards. My instinct is to do it backwards. And now this is an ideal, so we apply ideal.addMem. So we can guess what the ideal is. And now I want to prove that f minus g is in, we don't, that's the thing we don't have the proof of. Okay, HGS is what we have the proof of. In fact, it's refined that, isn't it? Not that it matters. So now I've got to prove that f minus g is in the span, and I'm going to do that by applying HD, the inductive hypothesis. So apply HD. See how many goals I've got. And I've got 4 goals. So I've got to prove that the degree is less than d. I've got to prove that f minus g is in I. And I've got to prove that f minus g dot nat degree is that. So the proof of that is REFL. So what does HD want? Where is HD? Let's try and find it. It wants a natural, and the proof that the natural is less than... so it wants a natural, a proof the natural is less than D, and then it wants a polynomial, which it's going to guess, and then it wants a proof that the polynomial is in I, so show g minus f is in I from, I'll tell you later, apparently it's f minus g. There. And now, what else does it want? And it also wants the proof that the degree of this polynomial is m. So now I'm going to put REFL. And now hopefully we've got a smaller number of goals. Now we've got 2 goals, and one of them is this degree is less than d. So that looks good because the degree of g is less than d, the degree of f equals d, and the leading coefficients are equal. So that should be fine. And this second goal says that f minus g is in I. I mean, so I could actually start proving this. So this is I dot submem, right? I dot submem something something. And now what? Now I've probably, now I've got 3 goals. Yeah, that sounds right. And the first goal is that f is in I, which should be a hypothesis somewhere. Where is the hypothesis that f is in I? There it is, it's HFI. HFI. And now this second one, I need to prove that g is in I, and g is in the span of S, you see. And I know that the span, so I can use HSI. So maybe I can use HSI here. HSI, and then HG, whatever it was called, HGS. Oh, brilliant! And so now I'm down to 1 goal again. I think that was a refine, and I should be able to delete this show from. I can just use the term directly. Wonderful. So now what have I got to do? I've got to prove that the degree of this thing is less than d, and that's going to be fiddly. Oh, or did I? Is that one of the things I just proved? I'm not sure that that's either of the things I just proved. How do I prove that the degree is less than d? So what I apply is going to be called nat degree LT. Have we got one of these? What's this? That's no good. That's no good. That's no good. That's no good because it's the wrong way. Ah, what's this? No. Hard luck. Okay, so how am I going to prove that the degree is less than d? So this is a bore, I guess. I guess I'm going to do... so let's rewrite... so I guess it would be LT if LE and NE. I could use this. And now I've got to prove the degree is less than or equal to d and not equal to d. So I guess I can split now. Sorry. And then another sorry. Which apparently needs a second bracket. There we are. So now what? I've got to prove the degree is less than or equal to D, and that's because that's the thing I did, right? That's apply this thing here. Apply nat degree sub LE. Wonderful. So let's apply this. And now, oh, I didn't like it. Oh, I see. Because it wants me to use transitivity. So refine LE trans and then this thing here. And this is complaining it wants to know what the polynomials are. So I'll give it, what were they, F and G probably. Now it's still complaining. Oh, it wants a proof. How about that? It's still complaining. Oh, how annoying. Okay, well, let's make the thing. So, what? Why doesn't this work? This nat degree sub LE, it wants P and Q, P, F, G. So it, what about that? How about that? Oh, there we go. That looks good. Great. And now I've got to prove that the max. Yes, I see. So apply max LE or something. That'll be called. Yes. And now I've got to prove what? Now I've got to prove that the degree of F is at most D, and so that's H dot LE, I guess. H dot LE. And now I've got to prove that the degree of G is at most G, and we know that. That's HGD. There. So this is exact this. There. And that can go over there. And now what's left? What's left is proving that the degree is not equal to D. I see. And you know what? If D is 0, there's a catch here. If D is 0, then this is actually true, right? Because the degree of the 0 polynomial is 0, the nat degree. So at some point I needed to deal with the case of D is 0 separately. So where do I deal with that? You see, that goal is not, if D is 0, that goal is not true. What about this? This goal is true. Okay, so this line is actually, I need to do cases D. And now I need to deal with the 0 case. And now hopefully the sorry will have a D dot suck it. Yeah, D dot suck, D plus 1. I see, and so now I can finish this with this thing here. So I should apply this. Let's see how that goes. Didn't like it. Oh, hard luck. Okay, well, let's do it. Let's deal with this D is 0 case first. So now here F and G have got both degree at most 0, and their leading coefficients are the same, and so I claim that F equals G. And so why is that? So this is now convert ideal.0 mem underscore or something. Yeah, now I've got to prove that F minus G is 0. So now I know I want to turn this into F equals G. So suffices F equals G, library search. What's it called? It'll be ec of sub x0 or something. It's even a rewrite. So we can rewrite sub x0. There. And now I've got to prove that F equals G. And how do I prove that two polynomials, I mean, this is a bit ridiculous. How do I prove that two polynomials are equal? I can check all the coefficients, can't I? Does X work? Yes, excellent. So I've got to prove that I've got to prove that all the coefficients are the same. And the coefficients will be the same because, so again, this is cases on J, right? Cases on J, and now the first one is rewrite HGF. That should do that one. And this one, the reason that these coefficients are the same is because they're both 0. And so I need coef x0. So rewrite coef x0 of degree, there you go, that'll work, of degree LT. So now what? Now I've got 2 goals, there we go. So let's rewrite it again. And now hopefully I should still only have 2 goals, yeah, because the first goal became 0 equals 0. So now I've got to prove that the degree, oh, I don't want this, I want nat degree. Is that a thing? Looks like it is. I don't want to, I've stuck with nat degrees so far. Great, I've got 2 goals. And now this one here, so Linearith will solve that one, I would imagine. It doesn't. That's interesting. Does it not know 0 LT suck? G dot nat degree is less than or equal to 0. So this is, I mean, this is refine LT of LE of LT, and then it was whatever it was. HGD. Oh, and then underscore. I should really be doing these in a. Did I have 2? Yeah, I've got 2 goals at that point. So let's do this properly. There. And now what? I've got to prove that 0. So that's probably called nat.0 LT suck or something. Nat. Oh, it's probably called j.0 LT suck. It is. Great. And now what is left? I'm going to prove f.nat degree, so now I can rewrite h, and then apply the same thing again. So apply nat.0 LT suck. That should do it. Okay, proved. And after that rather long diversion, we've now got to prove that the degree is not equal to d.suck. What was I doing up here? What did I think was important when I was running through this? Oh, I see. Right, coef x0 of ecnat degree. So why don't we do intro this? So we could do intro this. Intro h ec. And now I guess I could replace, so have h2 colon is, have h2 colon equals this thing at the top, coef x0 of ecnat degree. I could just apply it actually, couldn't I? Why don't I just apply there, and will it make me, it wants h ec, let's try that. There we go. Wonderful. And so now this goal looks provable, because I know HGF says that the coefficients of d plus 1 are the same. So maybe I could just use simp HGF or something. Will that do it? Yes. Marvellous. So we've now reduced the problem to the following claim in commutative algebra. I claim that, so now here's the sort of the, here's the sort of the messy part of the argument. I've now got to come up with, I've got f is a polynomial of degree d in I, and I've got to come up with a polynomial of degree at most, I mean it'll have degree d, of degree at most d, in the span of s with the same leading coefficient. And the idea is that we've proved that's a technical lemma that we proved already, not in Orcs ideal 2, we probably proved it in more Orcs ideal. It'll be this thing here. You see there, this says I can if I've got a coefficient, if I've got a coefficient in this Orcs ideal IN, that means, you know, the coefficients of polynomials of degree n. So, for example, I can use, you know, the coefficient, the leading coefficient of f. Then I can find a polynomial which is in some span, which is a subset of S, and the leading coefficient of this polynomial is C. So this is what I need to use, and the proof splits into two parts. So let's do by cases. Let's do cases. What will this be called? LE or LT? DN with HDN. HDN, how about that? Oh, rotten luck. What did I do wrong? Oh, there's something. I've forgotten a comma. Is that what's going on? Yes. Cases, yeah. The skip tactic doesn't do anything, and if the skip tactic fails, something's gone badly wrong, and the badly wrong thing was the missing a comma. So now, HDN here is the case that d is less than or equal to n, and HDN here is the case that n is less than d. Great. So let's go back to this technical. Where's it gone? That's not there. It's where is it? It's over here. Great. Oh my goodness me. It was here. So what's going on here is that this n is going to be our d, and you see that we know I is in the span of the generators at degree n. So if n is bigger than capital N, we're in trouble. But in this case here, so we're going to use this with d. So we don't even need that file. Why is that file open? We don't need that file. And let's get back to our proof. So if d is less than root of n, then, oh, so let me put that in brackets. Just let me check that. Yeah, there was an error. Okay, so in this case, we want to use this, right? Orcs ideal. So what does this thing need? It needs an ideal, which is going to be I, because that's the only thing it can possibly be. And then it needs a proof that something is Noetherian, which is HR. And then we need a proof that something is in an auxiliary ideal. So that will be the leading coefficient of show f dot coef d is in Orcs ideal ID from something I'll tell you in a minute. And now, great, we've got two goals. And how do I know that the coefficient of why is this true? Do we have some lemmas about this? Orcs ideal ID. Do I know? I mean, I suppose I could just do the. I could just use the definition. So do I have mem? Did I write one of these? I didn't write mem orcs ideal. Rotten luck. Hard luck. I don't seem to have written it. So okay, so we're going to abuse definitional equality. It's going to be pointy brackets, comma pointy brackets, I would imagine. Now we've got three goals. And what's the first of them? It wants the polynomial, so the polynomial is f, and then it wants some proofs. What proofs does it want? It wants that's the original goal. That's the thing we're working on. It wants a proof that f is in I and a proof that the degree of f is less than or equal to d. So that'll probably be called HFI, and this will be called whatever the what's the proof that degree of f is equal to d called? Is it just called H? Yes, H.LE. So now hopefully I've got two goals, yes. And the last goal is that the coefficient of x to the d in f is the coefficient of x to the d in f, so that's REFL. There. So now we have this exciting polynomial y, which we can obtain GHG. That's that. And so now we're going to use G. And now let's see what we've got to do. We've got to prove G is in some span, and we've got to prove that the leading coefficient of G, so maybe we could do refine G underscore underscore. Does that give us two goals? Yeah. I've got to prove that I've got to prove the degree of G is less than or equal to D, and that's because G is in this span. So I need to get hold of this span. You see, G is in the span, in the R span of a bunch of generators. Yeah, everything here's got degree at most D. Right, so I know how to prove that, and it's going to use the first part of HG. So maybe I should do HG span and then HG degree. So now what? Oh, was it degree H? No, this is HG. This should be HGF. So now I've got two goals, but what's this goal? What's this last goal? Oh, it's more. I've got to prove that G is in the span of S, and is that HGF? Yes, it is. So what needs doing now? I'm going to prove that the degree of G is at most D. So that's some work that I'm going to have to take. I'm going to have to use HGS to do that. And what's the other thing? G is in the span of S. I'm going to have to use HGS to do that as well. Okay, so this looks like two pieces of work. There. Right, yes, this all makes sense, doesn't it? Because the span of S will certainly contain things. Even the R span of S will contain things of degree bigger than D, because it will contain things up to capital N. So what's my goal? I've got to prove the degree is at most D, so I could change that to G is in, what was it called? MID or something. Is it called that? No, apparently not. What was M? M wants, it was an R. MRD, of course. There. So Y is, and I know that G is in the span of this, you see. And so it will suffice to prove, so I can revert. So suffices, what a do I really have to do this? Let's see if I can cheat. Let's revert HG. I don't want to copy down. If I revert this, I've got to prove that G is in the span implies G is in something else. So now if I can use span LE somehow, have colon equals, what's it called? Span LE. What have we got here? We want maybe submodule.span LE. So that's what I want to apply. And what does it say? Oh, it's an if and only if. So maybe apply submodule.span LE dot 2. That's worked. Oh, nice. So now I've got to prove that the set, everything in the set Has got degree at most d, and that should be easy because I'm going to rintro SHS, see what it thinks of that. And now what does HS say? Oh, that's not at all what I expected to happen. What have I done? I've got to prove that the image of something is a subset of this. Intro S, well that... No, bingo. S is a polynomial in R. Ah, I see. I was taking... I was taking the polynomial apart. So now S is in the image of something, so I should be able to do this, right? Sort of R, HR or something. Now I'm going to be rintroing things. Yeah, I was taking polynomials apart, otherwise that's not such a good idea. So HR says that R is in something, and then so now this is REFL. And now I've got to prove... What have I got to prove? Let's get rid of the lambda. I've got to prove that something in the lift has got degree at most d, and I'm wondering, did I prove that? Did I prove... I want lift LE or something. Lift nat degree LE. There we go. Now let's apply this. Apply that. Didn't work. Oh, because it's in a namespace. Let's apply that. And that did work. So I probably don't need to desimp, I would imagine. Yeah. There. And now, what have I got to do here? I've got to prove that G is in the span of S. And again, G is in the span of something else. But this is the ideal span. So I claim that, in fact, G is in the submodule span. So I want the submodule span to be at most the ideal span. Is that a thing? Submodule dot span LE ideal. No. I know what to do. This ideal dot span, if this ideal dot span is submodule dot span RX. Apply. Is there a span LE span? Did I just see what's this span LE span? That's not. I want span LE. This is what I want. I want exactly this. Can I just apply that? Yes, excellent. So now I've got to prove, and so now you see I can revert HGS and then apply submodule dot span. I assume this is what it does anyway. Span LE span, the thing I was just looking at. Won't let me do it. Well, what was it called? Span LE. I could have sworn I saw a span LE. Span mul span, that's no good. No? Oh, span mono or something it'll be called, right? Yes, span mono. And it doesn't like it. Why not, I wonder? Fail to unify that, really? Okay, well let's refine it, because refining is better at unification. Oh no, come on. Oh. This is bad. This is the R span. This is wrong. It's guessed the wrong. It's guessed the wrong thing. I think we want R and then polynomial R. And now, so now I need to do the refine or something. And now what's it complaining about? It wants the S. I'm not going to tell you the S. I'm going to do that. Oh, come on. That's the definition of ideal dot span. What? Oh no, it's not. It's Yeah, okay. Huh. This is a bit annoying. Well, why don't I just do... I could just apply this anyway. I'll do... Why does that happen? I must be doing some shortcut. There, because now I get the submodule span, and now I revert this. How about this? Oh, come on. I know it's... What about that? Phooey. I know how to do it. I would just want to cheat. Can I put G here? What more does it need? No. So well. Okay. So I need the revert here. What have I done? Where's the revert gone? Can I get rid of that? Does this work? Right. So what am I doing? The point is I'm going to prove it suffices. I claim. Yeah, so I can't remember. I'm sure I managed to do this before. We can do this first. We may as well apply this because that worked. What is making that happen? So now G is in that polynomial, and now yeah, okay, all right. Well, let's make the thing that we're trying to make. So have H2 colon equals this. So what does H2 say? Okay, I've finally given in. Let's H2 says for all S which is a set so what's the set going to be? Where's the goal? Ideal.span S. So I suspect that it's going to be S. Oh, S set polynomial R. Close bracket. And now what does H2 say? Exactly. Now can I apply it? I really want to apply it. And it's let me do it. Okay, great. And now I want to do this. And now I do refine submodule span mono. And now I want to use H2. So what do I know about G? So now do I revert HGS now? Revert HGS now. And now does this work? Oh, how annoying. Come on, why can't I get this to work? Let's apply it then. Ah, bingo. And so now I've got to prove, wonderful. So now I've got to prove that this thing is in S. So now it's all downhill now. Intros RHR. Oh, it's a polynomial, so maybe I should call it, I don't know, let's call it Y, HY. We were using Y for polynomials earlier. And now this can be rintros, and this could now be some other thing, RHR or something. Does this look good? Yes. And And that can be REFL, missed. That can be REFL. And now I need that R, and now I can just desim that. And now I need that it's in S. So change something is in S. There, and now I rewrite whatever it was called. Rewrite finset.mem union, and now I'm hoping. So now this is the. So now I'm hoping that this should be easy. I know that R is. I've got to prove that the lift of R is the image of the lift map R, but that's a D and that's an A, so it's going to be use D. Refine D underscore underscore. What have we got for this? This one I've got to prove that D is less than or equal to N. Do we have that? That's exact HDN. So this should be rewrite mem, what's it's going to be called? Mem range or something. Have we got mem range suck? Oh, we get that looks like a good one, doesn't it? What's that left us with? That's left us with D less than or equal to N, which is an assumption, so I can put RWA there, and that should do it. And now what's left here? Do it properly. Right, last bit. I'm going to prove that this is in the image of that map. Right, so it's R is in the generators, and I've got to prove that the lift of R is in the image of the lift map of the generators. So my guess is that I can use. Can I use something? What's it looking for? Refine underscore underscore. Let's try that. Oh, hard luck. What's my goal then? I thought my goal was a. Oh, so do I need to rewrite finset.mem image if or something? Yes, now it's an exists, and it's going to be A, right? So it's going to be exact A something. No, sorry, R. R. And now I've got to prove that R is in the generators, which is HR. And now I've got to prove that something equals itself, so that's REFL. And that is the end of the proof. So that's the case n less than or equal to D, and this proof will be very similar. So if D is bigger than N, sorry, that was the proof D less than or equal to N. If D is bigger than N, then I want to use this thing here. But I want to apply it not with. Oops. So this is wrong. This should show fco of n is in this from, and I'm not going to prove it. And I'm not going to prove that either by the looks of things. No, what have I done? Is that what I've done? Oh, phooey. Oh, I see. That's everything. What about that? Does that work? Yes, that works. So what needs doing? Oh, this is going to be called Y because it's not the right degree. It's going to be a polynomial of degree n, right? HYS, HYF. And now what does it want from me after that? It wants the coefficient of x to the n. Okay, that's a reasonable thing to want. from underscore. Let's do this. And then we'll put a sorry here, and I should be able to delete that. Is that good? Oh, I've got an error. What's my error? Type mismatch application. Oh, come on. By. Oh, this should be a by. Wonderful. Now I've got no errors. Great. I've got one warning, which is my indentations are not so great, are they? By. Why don't I do that? There, that looks nicer. Okay, so I've got to prove that the coefficient of x to the n is in this Orcs ideal ID. You see, and that by definition it's in Orcs ideal IN, right? But d is bigger than n, right? You see, look, we can rewrite. Yeah. So it suffices to prove, is f coef n in Orcs ideal IN? Do we have that? Oh, was that exact? That was exactly the thing we didn't have, or something. Do we know that f coef n is in Orcs ideal n? That's the lift stuff. No, I never proved that. Oh well, right. So I'm lost. Here we are. So maybe I should just get on with, I want to change Orcs ideal ID to Orcs ideal IN, and I can use it by HN. So I can rewrite left arrow HN, and now yes, it's in Orcs ideal too. But now I've got to prove that n is less than or equal to d. So that's probably HDN dot LE. Oh, it needs. How about that? Yeah, this is great. The power of dot notation. HDN has got type LT something, and they've defined LT LE to be the proof that if n is less than d, then n is less than or equal to d. So I've only got one goal. Marvelous. And now I want to rewrite it forwards. Rewrite HN forwards, and now R, because it wants to know the number. I'm going to use n. And now what? It wants to prove that n is less than or equal to n. So that's something like by refl. There we are. And so now I've got to prove this, and now this is the easy thing. So refine this. Is that going to work? Yes. It wants a polynomial, which is of course going to be f, and then it wants two proofs, and the first proof it wants is that f, oh my goodness me, it wants loads of proofs. It wants three proofs. I should definitely have made this a so it wants f is in I, which is HFI. There. Now what does it want? Now it wants the degree of f is less than or equal to n, and that's because the degree of f is equal to d, and hopefully, oh whoa, that's not true. This is the case that n is, this is the case that, oh whoa. I need to prove what? I've been led astray. What's the relationship between d and n here? N is less than d. So why is the coefficient of? Whoa. I've got this wrong. I must have. This is not what I want to show. I want to show f dot coef d is an Orcs ideal IN. Does this look true? Right, and now... Yeah, I've just got this the wrong way around. So I want to rewrite that way, and then write that the other way, and do them in a different order. How about that? Oh, bingo, that's working. Now let's look at my goals. Now I've got to prove the degree of f is the most d, and that's good because the degree equals d, so this is h.le. And now I've got to prove something which is hopefully REFL. Yes, this is REFL. Okay, great. So now I have this polynomial y, but it's got degree capital N. It's in the span of the lifted generators at level n. And so we want, and also I know that the coefficient, you see I want the coefficient of x to the d for g to be equal to the coefficient of x to the d in f. And this is problematic because it's the coefficient of x to the n. And so I need to define g, so I need to use y times x to the n minus d. Sorry, d minus n, right? There. And so now I've got to prove three things. You see, the idea is the degree of HYS will show that the degree of y is at most. Have I really got? Did I not prove something like this? Yeah, you see, we've got this. I just wasted my time proving this again, didn't I? Sorry. So let's refine this. That's what comes of doing things over a 1 week period instead of just doing it all in one sitting. Let's do this, and now we should have 3 goals. And the first goal, there. So have h2 colon equals whatever it was called. This thing here. That, because I'm gonna because I'm going to use it. I'm going to use that to prove that the degree of y is at most n. So maybe I should do, so have h hyn y dot nat degree is less than or equal to n, and then I can just apply this. And now let's see what I've got. After applying it, I have far too many goals. So this is HYS, so let me put HYS there. And now does that solve it? How annoying. It wants an ID, so I'll give it I. And now it's still complaining. It wants to prove that something's an Arthurian. And now it's stopped complaining. Great. So now we have that. And so now what we know, the degree of y is at most n, and the degree of x to the d minus n is at most d minus n, and so the sum will be at most d. So now this is, I guess we're going to do refine LE trans nat degree mul, right? Polynomial dot nat degree, polynomial is open, nat degree mul LE or something. Is there a nat degree mul LE? Yeah, that'll do. And then that. And now I've got one goal. I've now got to prove this. Great. So now the degree of that is at most n, and there'll be a lemma saying the degree of that is at most d minus n. And so we want to refine what will it be called? Ellie add Ellie or something. Or add Ellie add or something. Yeah, add Ellie add. Great. There. And then the first, oh, this is going to be convert as well. Convert add Ellie add HYN, and then I'm going to give it an underscore, unless we can guess. Unless we can guess what it is. I've got to prove this will be called nat degree x power L. Oh, is this one of the things I proved? Is this? Did I prove this in sheet 5 or something? Did I do this? It's going to be called nat degree pow x pow LE. How about that? And oh, it wants a nat degree x pow LE wants to eat something. What does it want to eat? It wants to eat R, and it wants to eat n minus d or d minus n, whichever one it is. So what have we got to do now? Oh, great. So there we go. Now I've got to prove that d is n plus d minus n, and my guess is that the ring tactic won't work, right? Yeah, it doesn't work. Isn't that interesting? And the reason it doesn't work is because this is natural subtraction, which is an evil thing. So maybe I will do replace hdn colon equals hdn dot le, and then try library search. Because if n is less than or equal to d, then that subtraction should be fine, and it'll be called add sub cancel or something. Oh, come on, library search. You know you want to prove this. Really? No, it doesn't. Okay, so let's play guess the name of the lemma. Oh, I suppose I could rewrite. I could rewrite add com, and then try library search. It might be that way around. Oh, okay, let's just guess it. Go on, 5 more seconds. No. Okay, I'll give in. So this will be called apply nat.sub add self. No. Add sub cancel. Add sub a sock, add sub bingo. That looks right. That looks, it's add sub cancel. Oh. Symmetry. Apply nat.add sub cancel. What? Come on. Oh no, it's sub. Is it sub add cancel then? Sub add bingo, and then we need hdn dot le. Let's get rid of those. Right, finally there. If only I knew the NAT API better. Right, 2 sorries to go. What have we got to do now? We're going to prove that that's in the span, and the reason it's in the span is because y is in the span, right? So that will be apply ideal dot mul right mem or something. Is that a thing? No, it's never heard of it. Mem mul right. Mul right. Is it really not mul right mem? Ah, mul mem right. Bingo. Because we don't care about the power of x. Oh, that's failed to work. Why did that fail to work? A is in I. Oh, does it need an underscore? Does it need another underscore? Does it need another underscore? Yes, it does. So now I've got to prove that y is in the span of S, and that is because y is in the span. I've done this. I've done this already. This is exactly the same proof, right? Where did I? This is here. Yeah, so this should be the proof. Where does it end? This should be the proof modulo the fact that some variables are called different things. So for example, HGS, oh yeah, so now I better sort out what's going on here. Is that good? That looks good. No, it doesn't look good at all. I've got unexpected token on line 203. That looks okay, great. Revert HR, and this needs to be unindented. What's that? That's like that. This is now HYS. Oh, and I haven't done the ideal dot span. I need to do the I need to do the line before. I need to do this thing here. Now what? Now maybe this will magically work. It did not magically work. I've got an error on line 200. I haven't. That's interesting. I was supposed to be proving that D is less than or equal to n. That's because I don't want to use. I want to use n here, right? And now that's compiled. Wonderful. So that's good. And now what? I've got to prove this, and so there will be a lemma about, what was that thing called about nat dot sub add cancel? Let's rewrite that. Is this going to go horribly wrong? Yeah, he's rewritten too many. I just want to rewrite the second one. So let's use n3 right. N3 right the first one, because we start counting at 0. And now, right, this looks good. And because now there's going to be some lemma. Did I mention this? No, I was too mean to mention it in the hints. So it's going to be called rewrite nat degree. No, it's coef, right? Coef mul x pow or something. Coef mul x pow. What does this say? See, that's perfect. That's exactly what I want. So let's rewrite that. Does it work, or do I need minor tinkering? I need minor tinkering. I need to rewrite add com by the looks of things. And now how does this work? This does work, and I've got to prove this, and that's exact HYF. And that, I think, is the proof of the Hilbert basis theorem. Marvellous. So that video was obviously much too long, and this proof was somehow still needs to be worked on, I think. But still, there we go. That's the proof of the Hilbert basis. There's MSc level commutative algebra in the lean theorem prover. Thanks very much for watching.